In part one of this talk, I defined what prediction is, what risk is, and I talked a bit about how we could learn a function that predicts something like risk. In this section, I'm going to talk a bit about how we actually verify a model to see whether or not the function we've learned is actually any good. So how do we validate a model? Well, Leo Breeman discusses the two cultures of model validation. We have this schematic here where X is a feature that goes into this black box of nature to produce a Y. And we're trying to model that process, model that natural process. In the data modeling culture, which is the one that most biologists are probably more familiar with and generally trained in, is we fit some sort of model and we assume some kind of null distribution for how Y is generated according to that model, and we use that to compute a p-value. Well, the algorithmic modeling culture is a lot more pragmatic. What it says is we have no idea the process that relates the input X and the output Y. But we can create some function, some algorithm that predicts Y from X, and we can just see how good it is in practice. So rather than computing a p-value, which we sort of interpret as some type of evidence against the null hypothesis, the algorithmic modeling culture will say the proof is in the pudding. And if the model works on new data and is accurate on new data, then we can trust that model is fairly reliable. Now, we talked a bit about the training data and the test data. In the training data, we know X and Y, and we use that to learn the function f. In the test data, X and Y are known also. In other words, they've been measured through some empirical gold standard. And we use the test data just to see if that function f is any good. Now, sometimes we don't have separate test data. Maybe our sample is a little bit on the small side. Maybe we haven't set up our experiment to collect a designated training set and a designated test set. There's another strategy people use for validation, which is called cross-validation, which is we take our whole data set, which is represented by one of these rows, and we carve out a fraction of it, in this case, a fifth of it, because we're talking about five-fold cross-validation. And we use 4/5 of the data as the training set, and that last fifth as a test set. Now, this test set's chosen randomly, and it could have a certain, there's a certain error involved with each of the predictions, and we want to get an estimate of the uncertainty around that error. So we repeat that process where we take a different fifth and use that as the test set, and the remaining 4/5 as training. We do that again for another fifth, and then another fifth, and then finally for the last fifth. So every sample in your data gets a chance to be part of a validation set. When we have 5 folds, we get 5 metrics, and we can get an average as well as a standard deviation for these. See, the test data should be used once and only once at the end to see if your model's any good. Now, usually the function f is quite hard to learn, and you need to try a lot of different functions before you settle on one that works. In this case, you need a validation set. Another data set you can use to update your function before you go to the test set. And a way we can think about that conceptually is we have our training data, again, X and Y are known, and we split our training data into 2 subsets, a training subset and a validation subset. Now, the validation subset, or sometimes called the validation set, is actually part of the training data. We're using it to tune f. So we learn some function of f, but remember these algorithms are quite complicated. There's a lot of arguments you need to choose and specify. Maybe the first ones you choose aren't the best. So you need to try a few different ones to see which one works. That's called tuning. Once the model's tuned, you can then go on, apply it to the test set, and see if your function is any good. If you're interested in reading a bit more about why the test set should be used once and only once, I have a link to one of our papers in the description below where we talk about this in quite a bit of detail. So test sets let us measure performance, But what is performance? Well, there are many performance metrics, and they depend on the nature of the output y. Generally, they all compare the predicted y hat, with the true known y, to compute some measure of difference between them. If y is continuous, well, the popular choices are to use something like a mean squared error, mean absolute deviation, or you can even use correlation if you'd like. Now, when you just have a single y, it's really quite easy to visualize this. What you can do is you can plot the actual y versus the predicted y, and look how much they agree with one another. When y is discrete or categorical or binary, it's more popular to use metrics like accuracy, specificity, sensitivity or recall, precision, area under the curve. And the majority of these come directly from a table known as the confusion matrix. So this can really take a while to wrap your head around. But the idea of a confusion matrix is that we have the actual class, as in positive or negative or whatever a binary is, 1 or 0. And we've got the predicted class, also positive, negative, 1 or 0. And we tabulate how often the predicted class agrees with the actual class or disagrees, and the nature of those agreements and disagreements. With this table, which contains the true positives, true negatives, false positives, and false negatives, we can compute a whole range of different metrics. Now, there is no perfect metric. Every metric imparts a certain perspective onto the data. So if you're going to be computing these metrics, I highly recommend you look at sensitivity, specificity, and precision. The three of those will usually give you a pretty good idea of how a model's performing. And the reason it's important to look at all of them is that there are cases in which you can have nearly perfect sensitivity, nearly perfect specificity, but the precision is awful, which essentially means your classifier or your model or your function isn't useful in practice. Now, it's worth commenting a bit about the AUC because for some reason, biologists love the AUC, which is the area under the receiver operating curve. And I get asked about this all the time. And I think there are two really prevalent myths with the AUC. The first is that you need it to evaluate a classifier. And that isn't true. Sensitivity, specificity, and precision are very good metrics in their own right and can be interpreted independent of an AUC. The second myth, which is much more pervasive and I think much more dangerous, is that the AUC is trustworthy for imbalanced data, and that is false. The AUC is no better for imbalanced data than accuracy is. And I'll include a link in the description from a really well-written blog post that contains an example that shows how the AUC can be misleading for imbalanced data. Now, when is the AUC useful? Well, it's useful when you want to know how a model performs over a range of cutoffs, not just at a single cutoff. Because what the AUC does is it compares the true positive rate versus the false positive rate for a number of different thresholds represented by these points here, and then computes the area under this curve between these two different metrics. And because you're getting the area under a curve across different thresholds, you're sort of getting an average of performance over a range of thresholds. And sometimes that's useful when you don't know what the best threshold ought to be. So now I'll talk a little bit about some common pitfalls in prediction. This is very much anecdotal and just what I've observed working in this field for a few years. So some of the most common mistakes I see are, first of all, reporting a validation subset performance as if it were a test set performance. This is a really big issue. The test set should be used once and only once, and shouldn't be used to tune your model. If you're going to be tuning your model, you need to take a part of your training set and set it aside as a validation set and use that to tune your model. Otherwise, the performance you get can be overly optimistic, which could mean that the performance suggests the model does work when it in fact does not work. The second issue is measuring AUC on imbalanced data. I've already given quite a bit of detail on this. The AUC is not reliable for imbalanced data, nor is accuracy alone. You must look at multiple performance metrics, especially sensitivity, specificity, and precision, and judge the goodness of a classifier based on the aggregate performance of all of those different metrics. The third issue, which is very much a biology health kind of specific issue, which is to not compare a biomarker tool against a demographic only tool. Demographics are often very powerful predictors in biomedical sciences. And it may be that your biomarker tool is also a powerful predictor because it's capturing information that's present within the demographics. So you should have a baseline of a demography-based prediction tool that you use to compare your biomarker-based prediction tool. The fourth issue is using very complex methods when simple ones are sufficient. In the same way in which I recommend you have a demographic-based prediction tool, you should also have some prediction tools that are very simple, like a line or a decision tree, and see how they do. And when you begin experimenting with very complicated methods like random forests or neural networks or SVMs, compare those performances against the performances of a line, against the performances of a decision tree, and ask yourself whether that added complexity is giving you bang for your buck. Now, the fifth issue I see, which is very pervasive in the field, is just having too few samples. Now, you need a lot of samples not only to learn your function f, but also to be able to test your function f and, when necessary, tune your function f. So really, it's hard to give a number to this, but I'd say you should be having on the order of hundreds to thousands of samples if you want to take the machine learning approach. If you have fewer than 100 samples, you might be better off taking the more classical statistical approach.